Okay, so we're back from spring break, and it is linear programming day 1 and 2. Well, of course, we're just doing day 1 of it. Linear programming is where you are graphing systems of linear inequalities. So basically, if you have one of those signs, you have an inequality. So you're going to have to translate from words into equations. So if I said the kid's age is greater than 6, A is greater than 6, you'd have to be able to write that. Of course, we usually typically use X and Y, but we're going to be having multiple equations like that and then graphing them. And if you have equations that have both X and a Y in them, like for instance this, X plus Y is greater than or equal to 7, you have to be able to graph the line, which we'd just solve it for Y and graph it. And then, for instance, say it's like that, and then it says greater than 7, you just shade above the line. So you're shading in a whole area on the graph. That's just a rough, example of what kind of thing we're heading towards. All right, so, of course, greater versus greater than or equal to. One thing that kids get confused by on this is that you can't be greater than and equal to at the same time. And you're right, you can't. You're either equal to something or you're greater than it. Ages are a weird one because we say that you're, let's say, 6 years old, even if you're like 6.5 years old, right? Because you don't say, well, I'm 6.7 years old. Actually, little kids are usually obsessed with how close they are to the next birth. Like, I'm only 4 days from my being 7 or whatever. But so if you're greater than or equal to something, I notice I said or. It's greater than or equal to. All right, so either you can be equal to or you can be greater than that. So number-wise, if we said greater than or equal to 5, here's a 5 on the number line. If it could be 5, I darken it in, and then I say like this, bigger than or equal to 5. As opposed to just bigger than 5 would look like this. Here's a 5, but I leave it empty. And that implies it can't be 5, but it be anything bigger than that. This implies it can be 5 and bigger than that. All right, so I think you already knew most of those rules. Simple one variable inequality from everyday life. There are more than 10 people in line. Did you write that using X? Yep, turn it back my way when you got it. You don't need the first sign, just the second one. You're not wrong, but you usually don't do a double sign. Good, 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 good. Yep, 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 yep. Yours. You can see it. Yep, that's right. And yep, okay, good. X is greater than 10 is all I was looking for. Why isn't it or equal to? Because it doesn't say or equal. It says more than. It can't be 10. You got to be careful on being picky on these. All right, so, of course, it looks like that. Now, what does the graph look like? You circle the 10, and then notice it's darkened in this way. Okay, so that's bigger than 10, but not 10. If I change it to or equal to 10, then I just have a filled in circle there. Okay, make sure you get the distinction between those two. If it's filled in, it means it can be that. All right, so here's one. Susan called to say the only tickets available for the Britney Spears concert are in row 10 or above, but less than row 40. Apparently somebody bought up all the tickets in the back rows or something. So maybe we have to be between 10 and 40, but this has something a little more specific. It could be equal to what? Could be equal to 10. All right, if you were to graph that, do you get it would go between 10 and 40, and it'd be darkened in on the 10. Does that make sense? Okay, good. Moving on. Two variables. So here's one with two variables in it. What looks weird about it? What do you think we should do? Add what? Subtract 4. I like it. Subtract 4. Everybody do that, please. And you'll be close to the answer, but you won't have the answer yet. Really common mistake is people think, oh, that's a negative 4, so I'm going to add 4. Wrong. That negative is on the y. So when we subtract 4, we're getting rid of the 4, and the 4 is gone. But you still have the negative. It's negative y is less than or equal to x minus 4. So now what? You can divide by a negative, or you can Come on, what's the other way to get rid of that negative sign? You can either multiply or divide by a negative. Okay, so this negative y won't be negative anymore once we multiply by a negative. I'm going to multiply by negative 1. Dividing by negative 1 would work also, but I think it's way easier to multiply than to divide. So I'm going to multiply by negative 1. What does that do? This negative cancels off, and now it's just y. And this negative gets multiplied by both parts. Notice we don't just pick one and multiply it by negative 1. We have to multiply both parts by negative 1. Y less than or equal to negative x plus 4. Get how both of them had to change? Now, there's a little something wrong here. Who knows what it is? Yes, sir? Yes, the sign has to flip. Why? Because I multiplied or divided by a negative, the sign has to switch. That's the number one thing that they check, like on the ACT, is did the kid notice that when they divided by a negative, they switched the sign? Okay, that's the thing everybody looks for on these. Because other than that, it's pretty much just solving equations. They're super simple. So now it's solved for y. If I was actually going to graph this, I would just need to graph this line. And a lot of people, we've done some complicated graphing, so they get like confused on how to graph this. It's not hard at all. Act like it's just or equal to. And then if I was going to graph that, do you get that the slope is negative 1 and the y-intercept is 4? So I'd have to go to 4 and have a slope of negative 1. Slopes that are negative go down. So it'd be down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Okay, so anyway, there's an example of graphing this, but it really isn't an equals. Part of it's an equals, but part of it's a greater than. So now how do I finish the deal? I've got it graphed and I shade where? Above. It says greater than, you shade above. That's all there is to it. If you always solve them for y, this will work. Some people try to like take this and then say, oh, well, see, it's a less than sign, so I'm going to shade underneath the line. You can't do it yet. You gotta solve it for y first if you're going to try to use that. Less than means below and greater than means above. So I'd have to subtract x from both sides like that. And now I can get y is alone, and now I can say, yeah, graph that and shade underneath it. There is one other way you can tell where to shade, and that's called testing a point. Would you agree that 0, 0 is on one side of my line? Here's my line, and there's two sides of the line, and 0, 0 is on one side of the line. You test if 0, 0 works. If I put 0, 0 in here, does it really work? 0 goes in here, and 0 goes in here. Is 0 greater than or equal to negative 0, which is just 0, plus 4? Is 0 really greater than 4? No, so you know it does not work. So you know you should shade on the other side of the line, because this didn't work, and therefore all the other points on the other side of the line, like over here, must be the ones that work. And so therefore you shade on that side. Now I personally just like the it's greater than, so I shade above it rule. And if you can do that, you're fine. If it's less than, shade below it. Greater than, shade above it. But there's one kind you can't shade above or below, and that's if the line looks like this. Do you get that there's no above that line? Okay, so what if it's greater than and the line's like this? Then it's not too hard to tell. Which way is greater than? Yeah, this way is greater than. So if there is no above it, then you go to the right of it. Okay, that'd be greater than. Same as if the line had been like this, we'd shade above it. If there is no above it, go to the right. Okay, so this is just a quick review of what we just did. We solved this thing, got it nicely solved for y is greater than or equal to negative x plus 4. Notice the sign had to switch right here. That's the most important thing to remember. If you ever multiply or divide by a negative, you have to switch the sign. Notice it's not about, is there a negative in the problem? That's a common mistake. Some people think, oh, I see a negative, I have to switch the sign. No, it's if you actually did multiply by or divide by a negative. Like here, it was multiplied by negative 1 on both sides. That made us switch the sign. All right, and then to actually graph it, you graph the line first, which is again going through the y-intercept of 4 and having a slope of -1, meaning down 1 over 1, down 1 over 1, down 1 over 1. That's slope of -1. And then I just have to shade on the right side of the line, which in this case is above that line. Okay? So that's your homework for today, is problems just like that. So let's talk about if you had to graph x equals 6. There we go. There's x is less than or equal to 6. Think about it for a second. Do you get how it's one of those straight up and down lines? And when it says less than or equal to 6, it's this way. Now, why is that red line still there? Only because they're going to put a bunch of them together. Because when these get more advanced, we graph like 3 things on the same graph and see where they all overlap. Now, let me jump to the ending here. There we go. This is what they look like when you've graphed 3 things and shaded in all 3 things. And where the shading overlaps, you get that thing called the feasible region. All right, so let's just look at this a little more close. What's different about this one than the other 2? And it doesn't say greater than. It says less than. Doesn't the other ones? One of the other ones said less than. Yes? It's the only one that doesn't say equal to. Good. Now what's different about it? It's a dotted line. Okay. So notice, if it says or equal to, this is a solid line. See, like the line right here? It's solid line. As opposed to this blue one, where there is no little equal to sign, then it's a dotted line. That means that the things that are on that line don't actually work. You know how the border line, there's on this side of the border and that side of the border, but what's the border itself? The border itself can either work or not work. On this kind, the borders work. If you're on the border, it is a true statement still. You pick a number that's on this border, like 4, 0, and you stick the numbers in here, and it works. Okay. So, bottom line is, if it says or equal to, the line itself works, and you use a solid line. If it says less than, then the line itself does not work, and you make a dotted line. Less than or greater than, as long as it doesn't have an or equal to. If it says or equal to, then you get a solid line. Here's a way to remember it. Look at the sign here. Does it have a little solid line in it? Yeah, it has the equal to thing. So if it has a solid line in it, then you use a solid line. This line right here is a solid line. Does this little sign have a solid line in it? No, and therefore you don't use a solid line. That's just a dumb way to remember. Maybe it'll work for you. All right, what is this thing called the feasible region? The weird thing about that little region is that any point inside there works in all 3 equations. It makes this equation happy, it makes this equation happy, and it makes this equation happy. So if I pick a spot like 4, 4, you get that that's 4, 4 right there? If I pick 4, 4, I stick it in here, here, and here. All of them will still be true statements. Okay, 4 is less than 6, so yay, I win there. And 4 is less than 8 plus 4, which is 12. Yep, 4 is less than 12. And then here, 4 is less than 0. No, 4 is greater than 0, sorry. 4 is greater than or equal to 0, and it is. So obviously that point works in all of them. Now, what we're going to go to when we're all done with this is we're going to give you a word problem. From this word problem, you'll be able to write equations. Once you have your equations, you graph all your equations, and you get what's called the feasible region. And then the final thing you'll have to do when you're all done with this unit is figure out which of those points gives you like the most profit or the least cost, and that'll be your answer. So a typical question might be, in a factory, we need to make more than 6 machines every day, but we don't have enough materials to make more than or we have to use enough materials to make at least 2 machines every day. And then you end up getting this set of equations from the words. You graph them, and then you figure out the answer. I'll tell you right now, will always be that spot, or that spot. The vertices of the feasible region. Those are the final. One of those is always the right answer. Okay, there's lots of points inside that feasible region, but only the ones that are on the corners are the ones that could be it. Yes, sir?
So in this case, just hypothetically,
yep.
It would be the bottom one, right? Just dotted line going through the other one.
Ah, interesting point. You make a good point that if this was the question, you're right that this dotted line here kind of messes that up because the corner doesn't have a solid line on both of them. That's a very good observation. And there's a lot of things wrong with this one being a real-world answer because it has negatives. Can you have -2 machines built? You know what I mean? So that one gets thrown out for that. And this must be like, maybe it's negative time or something. So anyway, you got issues with this one to be a real-world problem. But the point I'm trying to make is that you're going to have a word problem. It's going to give you equations with words. You have to make the equations. And then you're going to eventually graph this feasible region, and one of these spots will be the ones, you'll test them all. You'll take this point, and this point. You'll stick them into a formula. I'll show you how to write the formula. And then whichever one gives the right, like whether they want the biggest or the smallest answer. If it's biggest, it's usually profit because you want to maximize profit. And if it's like us really looking for a minima, in the minimum, it's because you're looking for a small amount of costs. So you either want to minimize your costs or maximize your profits. That's what businesses do. So, all right. That's the big picture. So now let's actually start your homework together, and I think you'll see these aren't too hard. This is just kind of like a preview of what they're going to look like. A word problem. It has a feasible region in here. And what did I tell you? Well, the answers would always be one of the corners, also known as starts with the V, vertices. These will be the answers. One of those will be the answer. And if you want to maximize, it's usually the one that's way furthest to the right and up. And if you want to minimize, like smallest amount, think about it, 0, 0 is pretty small, right? So it's the smallest answer is, if you're looking for a minimum, is usually the one that's to the lowest and the left. All right, that's just me trying to like pre-teach you the entire unit. What you really have to do for today, you just have to be able to graph something like this. So everybody try this one right here. And I'll start your homework with you right after we've tried this one practice problem. See if you can graph those 3 lines. Shade on the right sides of them. Decide whether they should be solid lines or dotted lines. Usually it makes a triangle if you have 3 lines. And you shade on the inside of it to get the feasible region. I'll give you a hint. If x is equal to 1, that's a line like this. It doesn't really have a normal slope and everything. So there, I've graphed that one. I just haven't shaded it yet. When it says greater than 1, I'm going to shade it just a little bit. Some people go crazy shading the whole thing like very carefully. Save that for the feasible region, the place where they all overlap. You can just do a little tiny bit of shading on one side of the line until you figure out where the rest of the lines are. This one, you're going to want to solve it for y. All right, I'm going to pause for a minute and give you a chance to try this. Remember, solve this one for y is the hardest part probably. Okay, I've got most people there. I'm going to make sure for those that are not understanding or those following along at home, here's how you do it. Y is greater than or equal to 0. Here's y is equal to 0. It's a line going along there. And where is it shaded? Greater than. So I'm just going to go slightly above it. The hardest one, of course, is this one. I subtract 2x on both sides. And even some of my best students will sometimes make that mistake and like try to divide by 2 there. Subtract 2x on both sides. Then wait, I don't have to divide by anything. It's done. I just have to graph that. And it starts at 6. 1, 2, 3, 4, 5, 6, right there. And it has a slope of -2. Down 2 over 1, down 2 over 1, down 2 over 1. And hopefully you'll see a line like that. Now, from here I just have to shade it in. And which way should that one be shaded? It says less than. So I shade under it. And where do they all come together? All the shading comes together right in there. That's what we were looking for. Any questions on that? That's the homework for today. That's all you got to do is a couple of those. Okay? So, everybody find your homework that's posted for today. I'm going to pause for a second while I do that. Okay, so here we go. Linear programming day 1. It says find the feasible regions and the coordinates of the vertices representing the feasible region. So basically you just got to like call out the corners of your shape when you're done. All right, so this first one, x is greater than or equal to 1. Here's where x is equal to 1. That's one spot where x is equal to 1. My smart ink is not working. It's not being very smart. Hold on a second here. Okay, I can't explain why it won't let me write on that. Pause for a second. Okay, here we have it. The only thing I could use some help on is, since I can't see it now, was it x on top? Was the first line x is greater than? Was the next one y? So it's x and then y, and was the last one y also? Okay, so then, to start with, x is greater than or equal to 1. I find 1. Here's 1. And that is pretty wavy, but it's harder on a smartboard. Well, I guess your iPads aren't that easy either. Greater than or equal to 1. So greater than or equal to is like this. Just slightly shade to the right. You don't have to shade the whole thing. I'm telling you, it's harder. All right, y is greater than or equal to that. So I start at the y-intercept is 1. The slope is the number on top of the x, or the in front of the x. So the slope is 1. So it starts at 1 and has a slope of 1. Okay. And that's supposed to be shaded greater than also. That's above that. So can you tell that so far my feasible region is right in here? That's my feasible region so far. But then I have a third one that's going to come in. Y is less than 8. So here's where y is equal to 8. I'll do it in blue. And then less than 8 means shade underneath that, right? So now, hopefully, you can see your final answer. This part I should erase now. It's my micro eraser here. Because I have to stay underneath that blue line. My final feasible region is right in there. And there is like a little funky corner on it, too. It's like the corner gets, I think. Let me see if, let me think that through. No, there's no, I think that was just a flaw in my drawing. There, it's just a triangle, isn't it? Okay, and then what are the corners, the vertices? You just got to name them, because it says in the directions to label them. So I should go like this and say, that spot is 1, 2. That spot is 5, 8. I think. Anyway, you figure out what the last spot is. That's an example. All right, now we can spend more time talking about your tests and stuff. So that's the homework for today. Linear programming is the general category. All you're really doing today is graphing inequalities.